For the materials and method used in the article, we discuss the sample preparation. As we can see from the image provided, that is an ultrasonicator which is used for the production of nanoparticles, a process called sonication. Ultrasonic frequencies greater than 20 kHz are usually used, leading to the process also being known as ultrasonication. After the solution were prepared, the PCl and PCl plus nanoparticle solutions were placed on glass molds into a glass vat for evaporation of the solvent, creating thin film membrane samples for different characterizations. The first characterization used is a scanning electron microscope or SEM. SEM produces an image of the sample specimen by scanning it with a high focused energy beam of electrons in a raster scan pattern. The electrons that interacts with the atoms in the sample produces signals that is detected by either a backscattered or secondary electrons detector. The signal contains the information about the sample's surface morphology, topography, composition, and other properties, and the image are seen at very high magnification. Sample image of the SEM analysis is shown. SEM was used for the analysis of fracture surfaces of the membranes and for the analysis of the tubular prosthesis. Differential scanning calorimetry is also used for characterizing the samples. A simple schematic diagram of a DSC shows how the equipment works. A pan with a sample polymer and a reference pan are both heated at the same rate, but the sample pan will require more heat since having an extra material will require more heat to keep up at the same heat rate of the reference pan. The data collected in this technique is used for studying thermal transitions such as melting temperature, glass transition, and crystallization as seen in a typical DSC curve. The last characterization technique used is a dynamic mechanical analysis or DMA. DMA is an important technique used to measure the mechanical and viscoelastic properties of materials such as thermoplastics, thermosets, and elastomers. In DMA, the sample is subjected to a periodic stress in one of several different modes of deformation, such as bending, tension, shear, and compression. In the schematic diagram of the DMA apparatus, it shows how the equipment functions. The force generator contains periodic stress such as tension, compression, and shear, which is applied in the sample while being heated by a furnace, making it stretch and compress repeatedly. So for the sample DMA curve of a PAT provided, it shows a plot of storage modulus G prime and loss modulus G double prime versus temperature. Modulus as a function of time or temperature is measured and provides information on phase transitions. Further explanation of dynamic mechanical analysis will be explained later together with the results of the data. Heading into the results and discussion of data, I would be interpreting the dynamic mechanical analysis. So, for further explanation, properties primarily measured in DMA are storage modulus or G prime, the ability of the material to resist deformation, and loss modulus G double prime, which is related to how easy the material can be deformed or how it shows a viscous flow-like behavior while being deformed. So the samples at different additives and pure PCl, polycaprolactone, and polycaprolactone added with NPC, which is nanoparticles of carbon, and PCl added with nanoparticles of graphene, which is NPG, and PCl added with NPC, NPG, all undergone cyclic loads at very low temperature to ensure that thermal effects on the sample are negated. giving a clean result. At the initial stage of 100 degrees Celsius, the shear modulus of each sample can be observed, and as seen from the graph, pure PCl has the lowest shear modulus or stored energy compared to the other samples because its density, given at 1.145 grams per cubic centimeter, is lower than carbon nanotubes and graphene, where carbon nanotubes and graphene are the NPC and NPG, and their density are around at 1.3 to 1.4 grams per cubic centimeter. Furthermore, PCl plus NPC has the high shear modulus, and followed by PCl plus NPG, and so on. As it was characterized using DMA, it is observed that at glass transition, PCl plus NPC and PCl plus NPG reach first at negative 61 degrees Celsius. This can be attributed to the fact that the average density of the sample added with NPC and NPG is smaller than the density of a pure PCl. The highest density would be the PCl added with NPC and NPG because it has the highest density. That's why it was the last to reach glass transition. From this, it is considered that additives mixed with the polymer makes the overall material much denser. Since denser materials have higher molecular weight, it results to a higher mechanical property, which corresponds to increase in glass transition temperature, Tg. Therefore, the denser the material, the higher is its melting point because material subjected to high temperature expands and denser materials expands less. From the graph, it is observed that pure PCl is less dense than CNT and graphene sample, that's why it was the first to reach glass transition. Again, PCl added with NPC and PCl added with NPG has the highest glass transition because it is denser, improving the overall sample's mechanical properties and the shear modulus. Although PCl has good mechanical properties, it has high crystallinity and it has a low melting point due to being the lesser dense component compared to CNT and graphene. Multi-walled carbon nanotubes and graphene, which is two-dimensional, used as an additive, exhibits excellent mechanical property. But by adding either NPC and NPG, the resulting microstructure of the composite improved, increasing the melting point or glass transition of the sample and increasing the shear modulus.